Good morning, good evening and good night, depending on which time you are going to observe this lecture. Welcome to the fifth lecture on solution chapter. In this lecture, we will be going to discuss about the vapor pressure in the liquid solution. We know the liquid solution can be prepared every time. In the liquid solution, solvent is always liquid, but you can change the solute. Accordingly, the liquid solution has been named after that. In this case, we are going to discuss the liquid in liquid solution, where both the solvent and the solute are liquids. So today's lecture is today we are going to understand how we are going to calculate the vapor pressure where both the components are liquids and both the components are volatile. So this is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. So how to calculate, how to determine the vapor pressure when there is two components are there and both the two components are the volatile components. For that, we have to take the example of a system having the binary solutions, and where we keep the solutions in the closed container. And when we keep the solution in the closed container like this, and there is both the component, we have suppose both the component are denoted. It is denoted by 1 and 2, and the vapor pressure of both the component, vapor pressure of at equilibrium, we say at equilibrium, vapor pressure of both the component, you can write both the component, you can see that is denoted, both the component is P1 and P2, and so total pressure P total, the total pressure above the solution, P total will be the P1 plus P2, and the mole fraction of both the components, mole fraction of both the components is suppose it is x1 and this is x2, both the components having the mole fraction in the solution stage, it will have the x1 and x2. There is a correlation between the partial pressure and the vapor stage of the two components, partial vapor pressure, with this mole fraction of this component in the solution. And this relation is given by one scientist, that is Raoult. This is called as the relationship is given by the Raoult, and this is called the Raoult's law. This is called the Raoult's law. Raoult's law tells about the relationship between the partial vapor pressure of the two components and its mole fraction in the solution. So what it tells, let us understand. It states for solution, let us write it, for solutions having the Raoult's law, it says for the solutions having the volatile components, partial vapor pressure of each component, you can see this is a word for each component, is directly proportional to the mole fraction of that component. So here there is a two components that you can see. So for component 1, For component 1, the vapor pressure is x1 and its partial pressure is P1. So we can write P1 is directly proportional to x1, and here P1 is, we can write P10 into x1. Here you can see one proportionality constant has been kept, that is the P10. What do we mean by this P10? P10 is nothing but the vapor pressure, we can write it, vapor pressure of pure component, vapor pressure at pure component 1, vapor pressure at pure component 1 at that temperature, At that temperature means in which temperature we are carrying out this experiment. This is the vapor pressure of the pure component 1. For component 2, we can write that P2, that is partial vapor pressure of the component 2, P2 is directly proportional to its mole fraction. So we can write this equation, P2 is equal to P20 into x2. Here P20 is equal to vapor pressure. We can write vapor pressure of pure component 2. Vapor pressure of pure component 2. So from the Dalton's law of partial pressure, we can write from Dalton's law of partial pressure, we can write the P total is equal to P1 plus P2. Now we put the value, both the P1 means P10 into x1 plus P20 into x2. Now we know x1, the mole fraction of component 1 can be written as 1 minus x2. So we can write P1 into 1 minus x2, P10 1 minus x2 plus P20 into x2, and it will be given by this formula. You can get this equation, we can get, that is P10 plus P20, we get this equation, P10 minus P10 into x2 plus P2 into x2. So you can further write P10 plus P20 minus P10 into x2. We get this relation. This relationship is this, that we get. We can write this, that is P10 total vapor pressure. We can write the total vapor pressure is, that we write here, P total is equal to P10 plus P20 minus P10 into P20 minus P10 into x2. This is the relation we get. P total is equal to P10 plus P20 minus P10 into X2. X2 is the mole fraction of the component 2. From this equation of the Raoult's law, we can conclude many important things that we are going to understand now. So we get this equation, that is P total is equal to, we get P10 plus P20 minus P10 into X2. We can conclude many important things from this equation. Number one, that total pressure, we can write total pressure can be expressed in terms of mole fraction of one component only. So we can write this very important conclusion, that we can write this expression, we can have, if we know the mole fraction of any component and we know the vapor pressure of the components, pure components, both the components having in the pure stage, then we can able to conclude at a particular temperature about the total vapor pressure of the solution. About the solution, we can easily able to see. This is a very important thing, that you can see this relationship has been expressed in terms of the mole fraction of the component 2. You can also convert with the mole fraction of the component 1 also. That is a very important conclusion. Second conclusion that we can take, that when we change the mole fraction of the component 2, when we change the mole fraction of the component 2, naturally the total pressure of this vapor pressure will also going to change. So we can write that total P total can change with the change of the mole fraction, of component 2. Okay. Third point, which components have the highest that can be shed from their pure vapor pressure of the pure components, and that will depend on the total pressure of this vapor pressure above the solution, that will depend on the pure components, vapor pressure of the pure components. That we can easily understand from this curve also. This is a plot. Here in the x-axis we are plotting the mole fraction. We are plotting the mole fraction, and here this is a vapor pressure. This is also a vapor pressure. So when x is equal to 1, the mole fraction of the component 1 is 1, means at the solution there is no component 2. That is the mole fraction of the component 2 0. At that time the vapor pressure will be P10, means vapor pressure of the pure component 1. As we goes on decreasing the vapor pressure mole fraction of the component 1 and increasing the mole fraction of the component 2, what will be the vapor pressure? Let us understand. This curve is for the vapor pressure of the component 1. We can write this P1 curve, that is curve 1. And when we are increasing the mole fraction of this component 2, component 2 is increasing, and here you can see x1 is 0, component, the mole fraction of the component 1 is 0 and the mole fraction of the component 2 is 1. At that time we will say this is P2, 0 means vapor pressure of the pure component 2. So as we increasing the mole fraction, we can see the vapor pressure of the component 2 increasing, and naturally the mole fraction of this component 1 is decreasing and its vapor pressure is decreasing. And what about the total vapor pressure, that we understand? This is the total vapor pressure. Total vapor pressure. So total vapor pressure we can see as the component 2, mole fraction of the component 2 is increasing, the total vapor pressure also increasing. This means here the component 2 is more volatile than the component 1 because the vapor pressure of the component 2 at the pure stage is higher than the component 1. So total vapor pressure, naturally we can able to understand that it depends on the vapor pressure of the pure component. If the pure component which is having the lesser vapor pressure, at the same time we are increasing its mole fraction, the total vapor pressure will going to be decreases. That you can see this is decreases as we increase the mole fraction of the component 1. As we increase the mole fraction of the component 2, it is increasing. Okay, I think that is clear to you. Now we are going to understand what about these two phase has been created, that you can understand what the liquid phase that we have discussed here, and there is another phase, that is the vapor phase. At that vapor phase, what will be the composition, mole fraction of the component 1 and component 2 that we are going to discuss now. Container, closed container. Here this is a solution phase. This is solution phase, and mole fraction is x1 and x2. And what about the mole fraction of the vapor component 1, vapor of the component 1 and vapor of the component 2? Suppose it is y1 and it is y2. So how do we calculate the mole fraction? This is the composition, we can write the composition of the vapor stage. Composition of vapor stage, composition of vapor stage at equilibrium. How do you calculate? Because from the Dalton's law of partial pressure, we know that the partial pressure P1 of the component 1 can be expressed its mole fraction with the P total. So we can write the Y1 is equal to P1 per partial pressure of the component 1 divided by P total. Similarly, for the P2, that will be Y2 into P total, and it will can be written Y2 is equal to P2 partial pressure of component 2 by total pressure. Okay, so we can able to understand the composition of the components at the vapor phase. If we want to know, if we able to know the partial pressure of the component 1 and component 2 and the total pressure at that time. Naturally, we are going to know this P1 and P2, we will to understand the P total also. So that is all for today's lecture. In this lecture, we have discussed a very important thing, that is the partial pressure of the components which are in the liquid and liquid in liquid solutions, where both the components are volatile components, and we understand the Raoult's law. In the next, we will understand in the next lecture, that is again a very important thing, that when we put a volatile, both the components are volatile, but if the one component is not volatile, at that time what will be the vapor pressure? Whether the vapor pressure will be same as the your component which is volatile or it is different, that we will discuss in the next lecture. Thank you very much for watching this lecture. Thank you.